Okay, that you can see this fine, I guess, or?
Yes, we are seeing clearly.
Okay, great. So hi, everyone. Maybe probably a lot of you haven't actually met me in person because I'm Chris Bourne from Suriko Sendai, but I actually have not been in Wako since before the pandemic, but hopefully I'll visit there in person soon enough. But yeah, so today the title of my talk is basically taken from an article by Mark Cass from the American Mathematical Monthly in the 60s. So can one hear the shape of a drum? And probably intuitively, we already have some ideas about this question, right? Okay, if I have a big drum, if I hit it, it will sound low. But if I have a small drum, it will sound high, right? But, we want to make this a bit more mathematically precise. And what can we say about it? And there's also this nice quote by Poincaré, which I thought was worth including. So if you can't read French, this basically says, so physics not only gives us the opportunity to solve problems, it also gives us methods of finding the solution. And also, by the way, this is me. So sometimes these old photos end up being useful later. Okay. So yeah, let me try and explain more concretely what we mean by hearing the shape of a drum mathematically. So we want to consider, a certain drum shape. So we have some 2D surface, which I'll call omega. So it's a drum, right? So there should be no holes or something like that in the inside. So it's a drum with a certain shape. And, when we hit the drum, the motion of the skin is what will give us the sound. And so how that motion is governed by, the wave equation, right? So we have F, which is dependent on the position, but also time. And the second derivative of F with respect to T is this Laplacian. So delta is, d squared dx squared plus d squared dy squared, or dx1 squared dx2 squared to be consistent. But really, okay, this is in general kind of a difficult equation, but what we can do is we can consider so-called harmonic solutions. So what we're going to do is we're just going to look at solutions that look like this form. And actually, from the perspective of both mathematics and music, this is all we really care about, because these are the pure tones. So all other sounds we can generate from these pure tones. And in which case, our PDE simplifies quite a lot. So we just have that this minus Laplacian F equals lambda F on your surface. And in particular, we want Dirichlet boundary conditions, right? Because the drum should not move at the boundary. So we have some eigenvalue problem, or what's the Dirichlet value problem for the negative Laplacian or the positive Laplacian on this surface. This is in general going to be quite hard to solve if you're not looking at like a rectangle or a sphere or something like this, or sorry, it's 2D, so I guess a disk. But that's not really what we're going to consider. But before we get to that, we can say a little bit more, because this Laplacian is an elliptic operator. We also know that it's a positive operator. So elliptic differential operators on these compact surfaces have very nice properties. So in particular, we know that the spectrum or the generalized eigenvalues are discrete, and it's positive. So we know that we can sort of label all the eigenvalues by just some numbers, or a discrete set of numbers, which we can order so that they are increasing. So the question is, can we hear the shape of a drum, right? So we're actually not interested in finding the spectrum. We're sort of considering an inverse problem. So if we know the spectrum, then what does that say about the shape of this drum? Because in theory, all the sounds that we hear from this drum come from this spectrum. So the question more concretely, okay, if we have two different drum shapes, omega 1 and omega 2, and they have the same spectrum for the Laplacian on with Dirichlet boundary conditions, then is omega 1 and omega 2, how closely, is there some sort of geometric identification that we can make between these two shapes? This is a very classic question, and in particular, anything that I talk about today, I did not do. This is just a very sort of gentle introduction to what you might call spectral geometry. Okay, so that's our problem that we want to consider anyway. But let's start out easy and just think about the one-dimensional setting. So what's a one-dimensional drum? Well, actually, it's just a string, right? And in this case, we have a string and we have this Laplacian equation, but in this case, it's actually pretty easy, right? Because it's just minus d squared f over dx squared equals lambda f for your eigenvalues. And, we're looking at a string with fixed endpoints. So f of 0, f of L is the length of the string. We just require it to be 0. But, I'm pretty sure most of us are capable of solving this equation. So we know what the solution should look like, right? They're going to be these sine wave type solutions. So we have a bunch of solutions indexed by the integers, or the integers minus 0 actually, of just these normalized sine functions, and we can explicitly solve for the eigenvalues. I mean, it's nice that you can sometimes actually solve these equations. So we want to hear the shape of a drum, or if you like, a string in 1D, but what is the shape of a string? The only information that we have is the length in terms of its geometric shape. But so long as we know just the lowest tone, or the lowest non-zero eigenvalue, then we know what it looks like. So we can just simply rearrange and get the length. So yeah, of course, we can hear the shape of a string, but that's not very illuminating, right? That's the reason that guitars work. And as you move up a fretboard, you expect the sound to change, and this is just a mathematical sort of confirmation of this very sort of obvious statement. So 1D things are kind of trivial, but as soon as we get to 2D and higher, then things get very, very hard very, very quickly. And actually, in particular, the statement is false generically in 2 dimensions. So 1992, Gordon, Webb, and Wolpert, they used some work from Sonata about certain results in spectral theory. And what they did is they constructed 2 different shapes. So there's no real obvious way to geometrically identify these two different shapes. But if you look at the Laplacian with Dirichlet boundary conditions on these 2 shapes, the spectrum will be identical. Now, these are maybe not the most normal looking drum shapes in the world, but at the same time, if you're allowing for any sort of potential closed convex shape, or not even convex, right, or at least simply connected shape, then you can build these counterexamples. So, okay, what if we consider more smoother options? So not without these corners or something like this. In 2 dimensions, maybe that's still open, but for example, we know that in higher dimensions that this is not true. So again, this back in the 60s, actually, Milnor showed that there was the existence of 2 16-dimensional flat tori, which are geometrically distinct, but who will have identical eigenvalues for the Laplacian. So even if we consider smooth type domains, at least in higher dimensions, we know that this doesn't work. But maybe somewhat surprisingly, there is actually some positive results, which is at least somewhat recently. So back in 2009, there was a paper on the archive by Hazari and Zeldich, but they consider fairly restrictive domains. So again, we're going to be looking at regions, this omega, with certain extra conditions. So convex, so any 2 points you can connect with a straight line. The boundary needs to be very, very smooth. So more than just regular smooth, it's actually analytic. So convergent series expansion. And also your domain should also contain at least 1 mirror symmetry. So, you should be able to have some sort of reflection symmetry of the domains that you can consider, and then some other technical assumptions, which I won't get into today. But what they were able to show is if you restrict yourself to this class of domains, then you can actually hear what you might call the shape of a drum. So if you have two such domains and they have the same eigenvalues, then they are going to be isometric shapes. So there's going to be a one-to-one mapping between the two, which preserves distances, which is about as good as you can get in terms of such an identification. Okay, so that's sort of just a bit of a historical overview of hearing the shape of a drum. But in the last 5 minutes or so, I just want to talk about why we even study such a problem and sort of the interesting ways in which, or what it tells us maybe about the ways in which analysis and geometry intersect with each other. Because physically, if you're a physicist, maybe this is kind of an obvious thing to consider. You have a certain shape and the spectrum is a bit like the energy or something like this. And I think if you were asked a physicist, I'm not a physicist, but I think people would say, you know, there's a geometric component to energy, or geometry affects the energy, but making this mathematically precise is not always so easy, because the spectrum or the eigenvalues are in general a very analytic construction. It's just about operators on Hilbert spaces or something like this. There's not necessarily any geometry that you're considering. Having said that, we find ways in which these two notions do connect with each other. And one very classical example is this what's called Weil's law. So there were lots of different Weils and they proved lots of different things. So this was Hermann Weil. So what we're going to do is we're just going to go back to our original problem. We have our Laplacian on our domain, and let's assume we know that there are eigenvalues. So we can consider this function, so n of mu, which is going to be the number of eigenvalues where you count the multiplicity, which are smaller than or equal to u. And then, you know, quite a long time ago, over 100 years ago now, what Weil showed is that if you have this information, this function n of mu, then you can compute this limit. So it involves n of u, just some various constants, and then the volume of the unit ball or the sphere. This is in Rn, sorry. If you can compute this limit, then you'll actually recover the volume of the original shape that you're considering. So on the right-hand side here is, again, just purely, well, I mean, apart from some constants, just purely analytic information about operators on Hilbert spaces. But here on the left, we have geometric information about the volume of a space. And so what this actually tells you is that, okay, maybe you can't hear the shape of a drum, but you can hear the volume of a drum, or its, you know, the area of its surface. Because if I know all the eigenvalues, then in principle, I can compute this quantity, so I can compute the volume. So Weil proved this, but then also conjectured that, you know, the perimeter, or, you know, the length of the boundary can be computed with a similar formula, which involves now both the area or the volume of the surface, also this function n of u, and some, you know, again, a limit. And this was eventually proved, though it took a long time, by Ivry in 1980. So again, this is telling you that I can hear the volume, and I can hear, or the area, and I can hear the perimeter of a drum. Can't necessarily hear the shape, though. And if you go back to this counter example, you can check exactly that these two shapes have the same volume and the same perimeter, because these results tell you that they have to. But yeah, we have this interesting connection where, on the one hand, we have geometric information, but we understand it with analytic information. And yeah, maybe just for the last minute or so, let me just talk about some other ways in which we seem to find this interesting connection between geometry and analysis, and this starts to get into the areas that I work in. So one quick example is what's called the Atiyah-Singer index theorem. Probably some people are familiar, where again, we're looking at these certain nice differential operators. They're elliptic of some differential operator on some manifold. Then you can compute this thing called the analytic index, and this is very roughly speaking, so the dimension of the kernel is going to tell you how many solutions this PDE has, just a linear PDE, and this dimension kernel of the adjoint is roughly telling you how many constraints are on the system. So number of solutions minus the number of constraints. This is just a purely analytic property of operators on Hilbert spaces. But you can compute this quantity using just the integral of a certain differential form that you can construct on your manifold, which you build using certain characteristic classes. So you don't have to really know what these things are, but once you have this information, you can build a certain differential form, you take its integral, and then you obtain analytic information about your original operator. And closely related to this point, so again, if we look at elliptic operators, we can sort of generalize what we mean to be elliptic. And then if we take a certain equivalence relation on these elliptic operators, then we can actually build a homology theory for certain manifolds or even just topological spaces. This is called K-homology. So again, just purely analytic information can tell you something about the geometry of, or at least in this case, the algebraic topology of what it is that you're studying. And lastly, so non-commutative geometry builds up this slightly more still, where there's now not even a space at all, but we're instead just using methods from geometry or topology to study certain operators on Hilbert spaces. And this also still turns out to be a useful way of trying to understand these various properties. But yeah, that's about all I wanted to say today. So yeah, thanks very much for your attention.
Okay, thank you very much, Chris, for very entertaining talk. That was a treat. Thank you very much. Okay, so any questions? Perhaps from the common room?
Yes. Can I?
Yes, go ahead.
So going back to the counter example which you showed, yes. So the number of corners are the same. I don't.
I mean, we can count them, right? In this case, yeah. I'm not sure. I actually don't know if that's important or not. Sorry, but certainly the area and the perimeter of the two have to be the same.
So there's no theorem for the number of corners.
Yeah, though, I mean, this construction relies on these results by Sonata about certain discrete structures. And so it might actually be playing in the background, but I would need to check the details to know for sure.
Yeah, follow-up question. So is it kind of angle of those corners counts, or it's possible that
I would, so yeah, I mean, you can now, I mean, this has been turned into a much larger industry where there are many sort of counter examples, but they all do sort of look like this, certain very simple shapes with these types of angles. So I suspect that, yeah, the angles of these corners is playing a role.
So any index, like summing up all those angles and the numbers of the corners, that stuff. That's something mathematicians is likely to do, I guess.
I can believe, but actually I don't know enough about the real nitty-gritty details of these counter examples to say for sure, but it's an interesting question though.
Okay. Any other questions? Yes, go ahead. Maybe come closer to the Maxwell.
If you find the structures, how will you find the structures?
These two, for example.
Yes, the key one.
I mean, it took a long time to make this counter example, so it was special in that sense. But yeah, it did rely on these results that were done a few years before that by Sonata about certain discrete Laplacians and understanding aspects of spectral theory in these types of situations where it's not so smooth. So I think once those results were in place, then you could start to I mean, you still have to be clever to write down these examples. That's definitely true. But once those results are in place, then you can start to explore a little bit more concretely and start to think which types of shapes might be relevant.
Okay, thank you. Any questions from the Zoom audience?
May I have one more?
Sure.
Yeah, so you consider only the elliptic operators, I mean, Laplacian type operators, but in 2D or any dimension, you can also, like like you can consider Dirac type first order differential operators. And is there anything that you can do if you consider some shape of the drum and then consider not only the elliptic operator, but also the other type of differential operators, so that the
so Dirac type operators are actually also elliptic, which is nice. So even first order operators are possible to study these sorts of equations. However, from the perspective of like shape of a drum, it becomes much harder because second order operators are usually bounded from below. So, okay, at least the spectrum goes to infinity, but at least it only goes to infinity in one direction, whereas a Dirac type operator, or just a, just for example, DDX or IDDX, its spectrum is the entire real line, or it's unbounded in both directions. And this makes your life harder in many ways, at least from the perspective of spectral geometry. Some parts, aspects of index theory are much easier for first order operators, but other aspects, so it's a little bit dependent on what it is that you actually want to consider.
I see. But in the physical application, it's really, I think sometimes we consider it's called the bag model. We have a sphere, and inside you have a Dirac operator defined, and then we need to calculate the spectrum of these operators to get the mass of the proton, the neutron, and so forth. There is a real application of this kind of thing. So that's why I was a little bit curious about it.
Yeah, I mean, first order operators should in theory be easier to solve than second order operators, and just from the perspective of PDEs. But yeah, I mean, this still doesn't make it easy, and you can at least get some information from the geometric quantities, but it is always going to be a little bit limited and a bit example dependent. But on a sphere, you might be able to say some amount of things, but I'm not sure how much I can say right now.
Next question. So if I understand correctly, so the disk we have a unique eigenvalue, right?
Chikai, could you come closer so that maybe it's closer to the microphone?
I think the question was if you
disk
have infinite eigenvalues, is that right?
I mean, if a disk, disk cannot have a unique eigenvalue series, right? I mean, there's no other manifold has a set eigenvalue.
I mean, I guess this is what this question is considering, right? Because we're asking about, if you know the entirety of all the eigenvalues, is it unique? How uniquely determined is this shape? And at least in some sense, it is kind of uniquely determined, but in general, it's not going to be, right? Because, for example, these two 16-dimensional flat tori, all the eigenvalues coincide, same multiplicity, all that information, but they are geometrically distinct shapes. I'm not sure if that was the question.
Yeah, right. But you have theory, the eigenvalue can determine the value and the circumferences, right?
I have what, sorry?
Where's my phone? So you have a theory, say eigenvalue can determine the area.
Right.
And the circumferences.
Right.
This one, right? So I asking if it was a disk because you determine the area and they have like a unique parameters. So I mean, there's no other manifold can have the same eigenvalue with disk.
I think for a disk, yes, because the disk is pretty nice and regular. But in general, no.
So no other manifold has the same.
I mean, so in some sense, that's what this result is saying, is that here the eigenvalues precisely specify the volume, the perimeter, but also the shape up to isometry. So in that sense, the eigenvalues do uniquely determine the shape of, or what type of object that you consider.
Okay. Okay, thank you.
I hope I answered that. Okay.
So it's related to Castan's question. So suppose that you consider many operators, and what's the point of considering only the harmonic operators?
Why just was it the harmonic oscillator or the Laplacian? Sorry, that you asked.
The Laplacian. You can consider any other elliptic operator and ask the same question.
Yeah, you can. I mean, there is something. Obviously, the Laplacian has some amount of importance, but yeah, I don't know how many other results there are about these types of spectral analysis for example, a Dirac operator, or maybe like some other second order operator. But at the very least, at least from the perspective of this index theory applications, you just need elliptic operators, and that's enough to get some information. So that does give you a fairly broad class of operators that you can study. Not all of them, but at least a decent amount.
So if you consider some other elliptic operator and also demand their eigenvalues to be the same, presumably that restrain the shape a lot more. Is that true?
Yeah, I mean, there might be some results about this, but if there is, I'm not familiar with them. But yeah, it would be interesting to consider if there is some sort of canonical or interesting operator to consider, and how much shape information is contained in its spectrum. But it's a hard problem, right? I mean, it took this result here took what, 30-40 years to solve after it was initially posed. So it's these are hard questions in analysis a lot of the time.
Okay, so any further questions? Okay, if not, let's thank Chris again for a very interesting talk. Again, thank you very much. Okay, so now I think those in the common room can just more informally chat with each other. Thank you very much.